Look here what I got you. You know how you've been having trouble knowing when to go to work? Being a watchdog now? I got you a watch. So you can tell time. You just have to, well, I don't know. You have to work on it a little. You're not, how are you going to learn to tell time if you don't pay attention? Now here, see? You got to look at the watch. See, get it lit up here. See? Now you can see that. I guess we better get you one of them talking watches. You're going to be late for work today. Well, thank you for watching Hillbilly Physics. This is a place where you learn stuff. And some of it's true. So don't get too carried away if I make a few errors, because I'm not a physicist, I'm a hillbilly. But it's like that little discussion I was having with my pup there. We're going to talk about time today. You know, back, 1200 or so, Saint somebody said that time and tides wait for no man. So you think time's pretty well fixed and don't move around, but that's not exactly right. We'll talk about that in a minute. I guess really if you want to start talking about time, you got to talk about Galileo. It's Galileo Galilei or something. Them Italians back then, they all went by their first name. Hello, kitty. My kittens or my cat in my lap. You're welcome. You just hop up. Galileo supposedly was going to church one time. Them fellas was pretty big on church back in them days, and Catholics, you didn't show up to church, you get run out of town. But, hello, Puss. This is Josephine, my kitten, my cat. She used to be a kitten. But, Galileo was in the church house, and there was a chandelier up there swinging. I don't know what started it wiggling, but it was going backwards and forwards, and he got to thinking, you know, it looks like it started out as swinging. It's going a lot further than it is now that it's slowing down, but it seems like it's taking the same amount of time. So, he didn't have a watch. He wasn't many of them around then. So he just used his pulse, and he timed that chandelier. And he noticed that as it slowed down, it still took the same amount of time to complete a whole swing. And that was a little interesting, because you'd have thought that the further it had to swing, the longer it would have took, but it didn't. It swung faster than his way out here. So well, let me show you about that. Okay, Puss, I'm going to put you down. I got to do some riding. You're a good kitten. Now you would think, well, everybody probably thought that before somebody pointed out it's wrong, but you'd think if you had a pendulum swinging here, and it had to swing from here, over here, and back to here, that it would take longer than it would if it was a shorter rope. And you might be right. But you'd also think that as it got closer down here, it would take less time. But that's not right. It turns out that this length right here, and the angle kind of throws in a little fuzz there when you get way up yard. Like if you've got a pendulum hanging here like this, and you take it all the way up here and turn it loose, it'll fall down. It don't work, see? So that's the angle here has got a little bit of the angle of the displacement's got just a little bit of variation on it, and in fact the strength of gravity has got a little effect on it, because if you're on Pikes Peak, you got more gravity of pulling down than if you're in Death Valley, because you got more dirt between you and the center of the earth. But then old Galileo, he got to figuring you could make a clock out of this, and they had to invent, they called it an escapement and to let it, you'd have some weights over here pulling on the thing, and it'd kind of give it an extra kick, and as long as the weights would start over here and they'd come down, and as they come down to here and it went up, you'd have to reset it, and have to have to wind your clock. Well, I don't think Galileo ever got the thing made. His boy took over the thing. Seemed to me like he worked on it, I read, 9 years. He never got done either. But that don't really matter. You have to say he invented the pendulum clock, which was the most accurate timekeeping mechanism they had developed up to that time. It sure did beat looking at the sun. Galileo, he was also right interested in being able to tell time if you're out in the woods or on a ship. So he also was looking up through his telescope. He made too, he's a pretty smart fella. He was by the way, he said, if you drop a big object and a heavy object and a light object, they'll fall at the same rate. And that kind of went contrary to what people like Aristotle had been saying all along. And he proved it, and he bragged so much about it and kind of insulted the people with real Aristotle-like supporters, and they, kind of run him out of town. He even got disowned by the church there for 300 or 400 years, I think, but they finally reinstated him back about 25, 30 years ago and let him get out of purgatory and go on to heaven. But that's not, back to this year, telling time out in the ocean. See, if you take one of them there measuring things, one of them there sextants, I think they call it, and you can look at the planets and the stars and stuff, and you can figure out where you're at on the globe. If you look at the globe like this, you can figure out where you're at, say here or here or here or here. But and that also goes true if you're crossing the ocean here. You can tell where you're here or up here or down here just by looking up at the stars. But you can't tell where you're at going this way. That's longitude. That was a big problem. Galileo worked on some of that there. He looked up there at Jupiter and he saw these moons going around it, and he kind of figured out if you could see what time it went over through here or started over here, you could have a pretty good idea what time it was, because as far off it is, it looks the same if you're in England or if you're in the middle of the ocean. So he got that. They even went as far as to some of them fellas calculated that and done a bunch of charts and tables, so you could take a reading of the stars and figure out where you was at north and south of latitude, and you could look at them moons going around through there and figure out what time it was, and reference that to what time they set back in London, or Greenwich Mean Time they called it later. You could figure out where you was at on the other side, then you'd know where you was right on the earth. But the trouble it was hard to get them measurements out there in the ocean with your ship wiggling and things, and if it rained for a few days, you wouldn't have any idea where you was at, and you didn't want to. You especially want to know pretty well where you was at, because you didn't want to go shooting around through there and run into America or somewhere and tear your ship up. So that was pretty important. And it was so important that the English Parliament set up a reward for anybody that could make an accurate timepiece that would work in a ship. See, them pendulums, they couldn't wiggle good because out there on them waves, so that didn't work out. And there's a fellow named John Harrison. He lived from 1693 to 1776. I don't know whether he was around here about what's going on over here at Declaration of Independence or not, but he, the English Parliament, they established a reward of £20,000. That's English money, not weight. And That's about $6 or $7 million in today's money, so that's a pretty good shot. And old John, he worked on it. They done that in 1730, and he worked on it for a few years. Then he come up with one that actually worked, and they put it on a ship and sent it somewhere, and when he come back, a clock was just off a few minutes or so. So that was good enough, and he worked and got it till it was even closer. And then, of course, like everything else, he had to argue around to get his money, but he finally got some of it, and I guess that's all right. It was fair enough, but usually when they promise you something, they ought to give you what they tell you. But I don't think he was too bad off, so I guess it worked out. So now, we know how to tell time, keep time. We know what time is, and we done heard that it don't wait on you, but it turns out that may not be right. Because a fellow named Einstein, you probably heard of him, he figured out that just through observation and, well, you know, the experimentation they were doing with particles and whatnot, atoms and all them little bitty things, he found out that, well, for instance, he come up with this thing called relativity, nothing to do with kinfolks. And let's say, this will give you an idea of what I mean by relative. Let's say you're on a train going down through here. Let's say you're on a train going down through here, and it's on a flat car, and you're standing here, and another fellow's standing over here, and you guys are throwing a ball at each other. And now let's say there's another feller, me maybe, is sitting over here looking over at that, I don't draw too good, do I? Looking over at that, them fellers throwing that ball, and this train, let's pretend like it's going that way at 50 miles an hour. And let's pretend like both of these fellas throws the ball at 50 miles an hour. You know, and their pitchers do 90 and 100 sometimes, so that ain't unreasonable. Let's say this guy throws his ball over through there at 50 miles an hour, and this guy catches it, and he throws it back to it at 50 miles an hour, and he catches it. Well, that's normal enough. That's just like playing ball, because everything's moving yonder way at the same time. The fellers are throwing it, and the fellers are catching it. The only thing is, this guy here is looking at it. Let's put some trees up here. There's a bunch of trees. He can't see these people. All he can see is this ball. And he's watching it as the train goes down through there, so he'd be looking and watching it going down the track. But what he'll see, because he's sitting still, this guy that throws it in the direction of the train, he sees this ball go shooting down through there at 100 miles an hour. That's 50 plus 50. And then this other guy, he catches it, and he's going that way at 50, and he throws the ball back this way at 50, so it just looks like it goes up. So what this guy sitting here looking sees the ball do this. And it's just shooting along at 100 miles an hour and then shooting straight up. You understand that? Well, that's got to do with that's being relative to where you look at it. These two fellas on the train, they just like they were standing out in the cow pasture throwing it. But this fella looking at it here, he sees it going a whole different way. Well, it turns out that they got to fooling around with them there particles and atoms and x-rays and things like that, and they found out that light, you could put it on a train and turn your flashlight on, and you'd see that light going at a certain speed, and the guy sitting on the ground sees it going the same speed. Now let's say you're Superman just whizzing along down through there, and there's a bullet right now, a shot out of a cannon or something, and it's riding on a light wave, and it comes down through there, and he sees it going at a certain speed. It still looks like it's going that speed wherever he's at, whatever, you know, it's relative. Now, I mean, it's constant. Wherever you look at a light going through at, you see it going at the same speed, and that don't make good sense. That don't make good sense, see? But they had to work out something. And they did. That Einstein fella. Now what Einstein worked out here, you know, you always hear the speed of light. I guess you hear that that's fast you can go, and it always thought, well, if light could just go a little faster, we could too. But it's really not, light is not setting the speed limit. The speed limit's just there. It just happens to be that light's the only thing go that quick. And here's what you got to do when you're thinking about speed. Velocity or speed is equal to the distance you go over how long it takes you to get there, the time. That'd be miles per hour, miles an hour, miles per hour, or however you want to look at it. But you see, when you say this year don't change, I mean that works good if you're driving a car and you're going 10 miles in an hour, you're going 10 miles an hour. Makes sense, right? But now, what if you set this one speed here that it's constant? This speed of light is constant, and you look at the distance. It's going wherever you're going to or from. It's going to be the same all the time too. So the distance is fixed. That means time has to change. Time has to be shorter or longer or something. And it turns out the faster you get, the slower time, the slower the clock ticks. And in fact, when you get up to the final speed, the top speed, the speed light can do, it turns out that time is zero. It's quit ticking altogether. You can't have any presence of time. So that's what I was trying to explain to the dog there. You need to learn how to tell time. But funny thing I just read, over in Warsaw and Poland, them fellas over there at the university has come up with an idea about what might happen if you could actually go faster than the speed limit, the speed of light, and how you might be able to do that. Now, I ain't gonna get into all that, but we always think of everything as three dimensions. So we got the three dimensions, up and sideways and out yonder way. Three dimensions. And time, we just think it goes in one direction. It's just got one direction. But you could change your mathematics. This is all pencil stuff. You could change your mathematics to where time has got three dimensions. Now I can't even picture that. And everything else has just got one. And then you can flip this here piece of figures upside down and kind of imagine what would happen in a place where you could go faster than the speed of light. Well, that's a little over this hillbilly's head. So I guess you won't be hearing much about that from me, but I hope you'll kind of think about this time thing and how it's progressed from a pendulum to a time machine, really. Thank you.